For the last 5 years, I've literally had something on my calendar that said, "Call Syracuse Lava Lab." It's one of the only places in the world where science and engineering and art meet to create lava, and it's something I've been waiting to do for so long. Well, guess what? Today, during finals week, we're doing it. So I'm here today at the Syracuse University Lava Project. I'm up here in New York checking out one of the only places in the world where scientists use heavy-duty machinery to make real lava. Yes, you could go to a place like Iceland and try to see what Mother Nature's already doing, but here at Syracuse University, they're controlling every part of the lava-making process, from what goes into the lava pouring rate, the slope, what they pour it on, and they allowed me here. Making lava isn't just as simple as heating some stuff up and see what comes out. As far as I understand, this crucible behind me was kind of a Frankenstein construction of different parts and pieces. Dr. Carson went to a number of different contractors, people who work with metal and rock, and he wanted to make this beast behind me. They thought he was crazy. This thing is sucking down many cubic meters of natural gas combined with all of these pipes to generate this crazy swirling vortex of temperature. When this lava comes out, it's going to be 1,500 degrees Celsius, which is well over 2,000 degrees Fahrenheit. So hot, in fact, that we can't really get anywhere near it, and it might melt our cameras. Hopefully not. But I've never seen a lava flow before in person this close. In fact, I think this is the closest anyone can really get to lava without actually igniting. The other thing is that you can't just throw anything into that furnace. Yes, pretty much anything will burn and or melt in that furnace, but what goes in is very important when you're experimenting on what goes out. They're getting some very specific basalt minerals from Wisconsin that they use. It's about 1 billion years old. They're using that to see how lava naturally comes out of volcanoes and ferromagmatic eruptions, as Dr. Carson tells me. They also need to put like heavy-duty steel down, or else it melts everything in the area. It's not all raw energy and fire and rock and heat and smoke here either. It's high tech too. You see this bullet time style of cameras they're setting up behind me? Well, this was put together by one of the students here at Syracuse University, and what it does is take still images and video in sequence so that later they can create a 3D model and spin-aroundable image of the lava. You see, you can't just take any old instrument like the camera you're watching me on and put it close to the lava to look at velocity and viscosity and another sciencey V word. No, pretty much anything would melt. So they have to have a camera system like that so that after the fact, they can see how the lava was looking and how it was flowing, and that informs everything that they're doing here today. After a lot of setup, I was about to check out the first lava pour of the day. What you notice immediately is, of course, the sound of the furnace, but the intense heat that comes out from the lava. Oh, wow, that's so awesome. Wow. What strikes you immediately is even though it doesn't look like there's a lot of lava here, it is so radiant with heat energy that you can't get anywhere near it. You can see Bob in the background there, and he's a pretty hardy dude, but this is as close I or my cameras could get because, like Dr. Carson said, it's like standing next to a bonfire, but a bonfire just distilled to its raw heat energy. And the bubbles that are forming there are from the moisture content of the sand. Even though the sand feels completely dry, the lava is so dang hot here, thousands of degrees, that any moisture content in the sand will immediately evaporate, turn into steam, and then push some of the lava out of the way, which increases the surface area and creates these otherworldly, beautiful bubbles. And just a few minutes later, it looks like the lava is almost all the way cool and it's starting to crack, but it's still extremely hot and might take hours upon hours to fully cool down. Now here is something I bet you have never seen before. This is a bubble made out of solid stone. This is a lava bubble, as Dr. Carson puts it, and it's something that's kind of exclusive to experiments like this. So when the super hot lava runs over the sand, even though it doesn't look like it, there's still moisture in that material. This moisture evaporates and pushes the lava outwards, spreading it out, creating more surface area, and this increased surface area cools it down very rapidly, which forms these bubbles. Now, these are just a few atoms thick. Literally, these can almost float on the air. They sound like pieces of metal when they hit a surface, which kind of makes sense because there's a lot of metal and minerals in this. And what you can learn from a lava bubble like this is, if you look closely, you can see how the bubbles of gases are expanding, how thin the lava bubble gets, and that tells the scientists here at Syracuse everything from viscosity to velocity, and it's kind of analogous to what happens in other lava flows around the world too, where if lava is confined in these bottlenecks of volcanoes, the gases expand, but then they explode, these bubbles rupture. So getting them crystallized and forevered is the technical term. Like this, you can see things that you can't really see anywhere else, and they're very delicate. Take that.
Yeah, I think one of the cool things we can see is how the water vapor from the sand has expanded and blown these beautiful lava balloons. And that's the same thing that's happening inside of volcanoes, like in Iceland, where you see fire fountaining, the lava shooting up in the air. It's because bubbles and gases are expanding like that, but all those bubbles are bursting. It's all the just pieces of bubbles are flying up in the air. Here, it's cooling off, and things are rapidly, so the glass is forming, it's still intact. And also, it's unconfined. It's not just stuck in a bottleneck, like in the volcano. Here, it's just wide open, so the bubbles can just expand as much as they want. But it's kind of a race when they form, because the lava's getting stretched. You can see the stretch marks inside the bubbles here. The lava's getting stretched as it cools, and they're still expanding. So eventually the bubble will break. My name is Jeff Carson. I'm chair of the Department of Earth and Environmental Sciences here at Syracuse University.
So this is the Syracuse Lava Project and Lava Lab. How did all this get started?
Well, it basically started one day when my colleague, Bob Wysocki, who's a sculptor and an expert in foundry processes, walked in my office and said, hey, I want to make some lava. Of course, I thought he was crazy. But after we chatted for a while and realized that he had the expertise and the equipment to do it, we just started melting some ancient lava and pouring it out to make our own lava flows.
Does your research align with studying lava as well? Were you interested in this before he made a giant furnace fueled with a lot of natural gas?
Well, it doesn't align perfectly. I'm basically a structural geologist. I'm interested in rift zones and mountain belts and things of that nature. But I immediately saw how what Bob was proposing would allow us to make lava flows under a controlled situation that was between the scale of investigation that was going on, between people who were studying real natural eruptions and what people were doing in laboratories. We're sort of in between at the sort of meter scale. We've been doing it for about 11 years now, and the project has grown and evolved in all sorts of complicated ways. We started out using a relatively small furnace with a crucible that's about the size of a 5-gallon garbage can, and just pouring the lava out manually indoors. We graduated to a much bigger tilt furnace that has a crucible in it that's almost the size of a bathtub, and we can pour out a couple 100 pounds of lava at a time, and of course that one's outdoors.
After the lava flow is sufficiently cooled such that you can handle it without your hands setting on fire, some of the students here at Syracuse start breaking apart the lava flow and cleaning it, because you can use the same material that was once molten just a few minutes ago in the next pour. You can recycle just about anything. And when this volcanic glass, this obsidian, is hardened, it is absolutely beautiful. You can see how the lava flowed. It is now frozen in time, and the edges of this stuff are just a few atoms thick. It can slice you like you were, I don't know, trying to cosplay as an Asgardian god or something. This is more or less the only place in the entire world where you can find artificially made lava. This took a number of scientists, number of artists like David, who we've been talking to, who put this all together on a shoestring budget to create situations and experiments that you can't do anywhere else in the world. In fact, some of the results have been so interesting that other geologists and geophysicists have been like, nah, that doesn't happen. But it does! While the outside experiment gets reloaded, the indoor furnace, this hellmouth looking thing, is now ready to go to pour on a different surface with different materials. All the operators for this indoor version of the lava pour experiment have to wear these suits to get anywhere near it, because these suits block the intense infrared radiation. Now keep in mind, as you might be able to see from the incredible glow of everything they're touching, this is just about as close as you can possibly get without melting cameras and burning your skin off. And look at the color. The lava here is so brilliantly hot, so many thousands of degrees, that our cameras can hardly tell the difference between what is pure white and what is just hot lava. Oh, it's so damn hot.
Right around 11:50. Cardboard behind you, Jeremy, behind you, grab the cardboard. I got it. How's it look sense-wise? I got it.
One thing that you don't realize unless you're right up next to lava is just how much heat energy it carries. Yes, you know lava is very hot, but this lava flow, though it may be small, has so much heat energy that this is going to take like 24 hours to cool down. It's 1100 degrees Celsius. It's so hot, in fact, that this steel plate it's on is currently warping. It is bending because of the expansion that it's causing on the top. If the top of the metal sheet expands, that means it's going to curl downwards like this, right? And so you can see just how much it's heating, cracking, bubbling, breaking. Lava science is awesome. What are the advantages of studying lava in this way, especially for geology and science in particular? And what can you really control when you're in here?
Yeah, well, there's a number of advantages. Number one, it's a lot safer than being around an active volcanic eruption.
Sure.
And, you know, that turns out to be pretty important because you can focus on what's going on right in front of you instead of worrying about dying. The other important thing is in a natural eruption, you just get what nature gives you. The slope, the composition of the lava, the weather, everything is out of your control. Here, everything is under our control. When we use the same composition lava all the time, we can control the slope that we pour it down, the temperature that we pour it at, how much moisture is involved. Basically, we're in control of all those parameters, and we can vary them a little bit at a time to see how they affect one another and the shape of the lava and its behavior.
How many other places in the world do anything like this?
Basically none. I mean, there are a few places, a few museums that will heat up some lava just to show that rock can be melted. Places like Hawaii, for example, don't do that. But there is one place, actually in Iceland, a place that my colleague Bob helped build with a smaller tilt furnace where they have an exhibition where they show people that you can make a lava flow.
So that sounds like the only people in the world who do this are you and Bob.
Right.
That's fantastic.
You know, I think we learn something new every time we pour the lava. Something happens that's a little bit different from what we expected, which is, it keeps it interesting and really fascinating for us. But I think when we see sort of bubbles forming in the lava, sort of balloons, I think that's one of the things that gets a lot of oohs and ahs.
Yeah, it's really beautiful, and it makes this. It's so counterintuitive because how thin the bubbles are. When you touch them, they make a sound like you're hitting like some tin foil or something like that. It's just because of the mineral content and stuff in them. It's very odd for what we consider bubbles to be.
Yeah, it's weird, dirty glass.
What are some things to look out for when you're doing a potentially hazardous experiment like this? I know you may have gone through a couple of cameras before.
Right. I mean, just anytime you're dealing with really high temperatures, I mean, it's pretty unforgiving, really. On the other hand, it's really no more dangerous than being around a campfire or a wood-burning stove in your house. If it feels warm, you just step back. It's not a big deal that way. The only real danger is when there are fluids around. If there's water that can be trapped, if the water is trapped and turns to steam, it expands instantaneously by 1,000-fold in terms of volume, and it can carry chunks of lava with it. So there's the possibility for that kind of splattering of lava to take place. But we're very careful to dry the sand out, make sure that we pour the lava over, try to make sure we never have that confined water.
For the last pour of the day, Dr. Carson and his team wanted to go all out. Not only pour on top of an already substantial lava flow, but tip the crucible until they released the molten metal they suspected was gathering at the crucible's bottom. They suspected that the impurities in the materials they were using were being sort of filtered out by the heat, having a different density and different chemical composition, mean that they were separating from the rest of the lava and accumulating at the bottom, and they wanted to see if they could get that out.
a lot. Oh no, no.
That's awesome. Oh, where's the metal?
And we're gonna start backing up a little bit.
Yeah.
Start backing up a little bit. Dang. This is the biggest flow I've ever seen you do.
Good size.
Well, on this one. Oh yeah, different color too. Oh wow, it does come right out underneath. Everyone. That's very cool.
I think we're good.
As you can see, they did indeed confirm their suspicions. There was molten iron at the bottom of the crucible, and because this iron is 3 times denser than the lava already poured, it instantly sinks to the bottom and flows, not like the syrupy lava, but like water, and beneath the lava itself. Do you see that? It's so weird. It looks so much different. It shows that even when you're dealing with something incredibly hot and incredibly dense, the interaction between these two materials can be as mundane as an interaction between water flowing under oil. It's just a density and viscosity difference.
It's counterintuitive that lava can be so hot and so potentially dangerous, but the way the physics of lava works, it can produce some interesting results.
Right. Yeah, the conductivity of the lava it plays an important role here. And for example, we used to have an apple tree out back, and we occasionally pour the lava onto an apple. And one of the things that happened was the lava solidifies around the apple, which is at room temperature. The lava's at over 1,000 degrees, but when it solidifies, that rind of solid lava is a really good insulator. So the apple doesn't really cook inside very much at all. We did the same thing with an uncooked chicken from the grocery store before. Poured the lava into the cavity of the chicken. It smelled great. We were going to have the lava chicken. It was going to be great. We're going to put KFC out of business. And instead, it made this exact mold of the shape of the inside of the chicken, and the whole chicken remained essentially raw.
Wow. What do you think would happen if I threw the One Ring from Lord of the Rings into the lava?
Well, it depends on what the ring's made of.
Titanium.
If it's made of titanium, I don't know the melting temperature of titanium right offhand, but if it's, if the melting temperature is less than about 1,200 degrees C, it's going to melt.
And we can finally destroy Sauron, is what you're saying.
Well, it could be done. But we're kind of doing an experiment like that right now, where we're throwing iron in with the basaltic lava, and they're just fundamentally different materials in a way. I mean, they're kind of at the same temperature, but the iron is very dense and its viscosity is very low, so it's very runny. So it sinks right to the bottom of the crucible. And it's sitting down there. It separates like salad dressing, like oil and vinegar. And so we're just pouring the basalt off the top like that. But our experiments later this week, we're going to pour both. And we want to see them come out and tumble and mingle together, as we think can happen on some planetary bodies.
You've been doing this for 11 years. Been working with lava, pretty much the only people in the world that do this kind of thing. If there was one takeaway you've gotten from doing all this, or one amazing thing that you've learned or grown to appreciate, what would that be?
I might say there are two important ones. One is that when you start from scratch in an area that is not set up for funding with the funding agencies or for publications. People just aren't used to it. They don't know how to react to it, and it's subsequently taken us about 10 years to kind of get to the point where we're publishing papers in the high-end journals. 10 years. That's amazing. Wow. That's a long time. So it wouldn't be too good for someone just starting out in science. For someone near the end of their career like me, I can afford to do those sorts of things. The other thing is just experiencing the completely different perspective on what we're doing, mine compared to my colleague Bob's.
Sure, the artist and the scientist.
Artist and the scientist, and our reward systems, the way we live in the academic world, the way we teach classes, the way we explain to people what we're doing with the lava, it's just totally different. It's like we're from different planets.
I've never been to the edge of an active volcano or gotten anywhere near something this hot, so it was an absolute pleasure to finally fulfill my 5-year-long dream of traveling to Syracuse University and seeing this real lava up close. Dr. Carson and his team are doing some absolutely fascinating science experiments there that aren't happening anywhere else in the world. It's a wonderful combination of art and science coming together to solve each other's problems to create something beautiful in both presentation and data. As the kids say, the science going on at Syracuse has both drip and a lot of heat. What do they say? You don't know. Shut up. Thank you so much to the very nerdy staff at the facility for their direct and substantial support in the creation of this here video. Today especially, I want to recognize Research Assistant Vorpelfish and Visiting Scholar Vikinger. If you want to join the facility, if you want to drape on apparently a crypto bro leather jacket, if you want to talk with me every day on Discord, see videos early, see private members only live streams with me, not like that. You can go to patreon.com/Kyle Hill and join the facility staff today. And hey, if you support us just enough, you get your name here on ARIA here each and every week here. And as you can see, there's literally hundreds and hundreds of you, so I have no idea how I'm going to pass this. Thank you again to Dr. Jeffrey Carson for having me out to Syracuse. It's a lovely city, an awesome science project that doesn't happen anywhere else. It's a lovely combination of art and science where an artist and scientists and geophysicists had to work together to Frankenstein this furnace and come up with new ways of looking at lava and creating it and what goes into it. I had a wonderful time. Thank you so much for having me. My sunburn from the lava has now subsided, so I can't blame you for that anymore. Thanks for watching.